Today I'm going to talk about a new type of function called a vector-valued function. The input for that function is going to be a single variable t, but the output for that function is going to be a vector. So if we have a function r of t, it will have, say, 3 components. Those components will each be functions x of t, y of t, and z of t. So you can see that the domain of this function will be a subset of the real numbers because our inputs will just be a single value t, but the range will be a subset of R3 because our output is going to be a vector in 3 dimensions. So let me show you a couple of examples. First, let's look at the function r of t, which has an output vector cosine t, sine t. And this should actually look familiar because if we think about t as being an angle, then the point cosine t, sine t, for different values of t should define the unit circle. Every point on that circle can be thought of as cosine t for the x coordinate and sine t for the y coordinate. Another example that is useful is the curve r of t equals cosine t, sine t, and say 1/10 t. The cosine t and the sine t, which represent the x and y, are still defining the unit circle, but the z component is now going to move upward. So we could have a circle that starts here at x equals 1, okay, and you could see it moving around, but as the circle is moving around, the height increases slowly, and we get a curve that looks like that, and that is called a helix. So basically, you want to understand that at each time t, that defines a point x of t, y of t, z of t, and if we let z vary, then that will give us a curve in space. Now that we have functions that are vector valued, we can talk about things like limits and continuity. So we will define the limit of a vector valued function, say r equals f, g, and h, where f, g, and h are functions, as the limit as t goes to a of each one of the components. So limit as t goes to a of f of t, the limit as t goes to a of g of t, and the limit as t goes to a of h of t. So we find limits for vector valued functions by finding the limits of each of the components. Once we have limits, we can talk about continuity, and our definition for continuity will be the same. A function r is continuous at a point if the limit as t goes to a of r of t equals r evaluated at a. In other words, we can say that r is continuous if its component functions f, g, and h are also continuous at that point a. And we still have this intuitive notion of continuity that if you can draw the curve, maybe like the helix that I drew for you earlier, if you can draw that curve without picking up your pencil, then that curve is continuous. Once we have limits and continuity, then we can start talking about differentiation. We'll remember that the derivative of a function f of t from the real numbers to the real numbers is just the limit as h goes to 0 of f of t plus, I'm not going to use h, I'm actually going to use delta t. So t plus delta t minus f of t over delta t. And so if we want to find the derivative of a vector valued function, then we could do the same thing. We could do the limit as delta t goes to 0, and we can take that vector valued function r of t plus delta t minus r of t and divide that by delta t. And so the definition is similar. Now, how will we then find derivatives of a vector valued function? Well, if we have a vector valued function r, which is equal to f of t, g of t, and h of t, where f, g, and h are differentiable functions, then the derivative of r of t is just the derivative of each of the component functions, f of t, g of t, and h of t. So we find derivatives by just finding the derivative of each one of the components. Now, why might that be true? Well, if we're going to prove a statement like this, we want to start with the definition of the derivative, the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. Well, that is the limit as delta t goes to 0 of each of the component functions. So f of t plus delta t minus f of t over delta t, g of t plus delta t minus g of t over delta t, and then finally h of t plus delta t minus h of t over delta t. Okay, so how do we find the limit of a vector valued function? Well, we take the limit of each of the component functions. So we're going to have the limit as delta t goes to 0 of f of t plus delta t minus f of t over delta t. The limit is delta t goes to 0 of g of t plus delta t minus g of t over delta t. And finally, the limit as delta t goes to 0 of h of t plus delta t minus h of t over delta t. And that limit of each one of the component functions you see is the definition of the derivative. So we get f prime of t, g prime of t, and h prime of t. You should note that the derivative vector, the vector that we just computed, will be tangent to the curve defined by a position vector r of t. So we want to look more closely at what does the derivative actually look like for one of these curves. So I've drawn a curve here in blue in 3 dimensions defined by the vector valued function r of t. You should note that there is a vector that's always kind of pointing to the position r of t. And then what I'm going to do is I'm going to look at another position a little bit further along, say r of t plus delta t. Okay, and of course there is another vector that's pointing to that position. Okay, we know that r of t plus delta t minus r of t. Okay, so remember, we're going to be looking at r of t plus delta t minus r of t. We're going to be looking at that vector. And we know from doing vector subtractions that that's actually going to be this vector right here. Let me go back one here. It's going to be this vector pointing in that direction from r of t to r of t plus delta t. And then if we take the limit as the denominator delta t goes to 0, what we end up with as we move the r of t plus delta t point closer to r of t is a tangent vector to that curve. Okay, so that is the derivative of a vector valued function, and the derivative is always going to be tangent to that vector valued function. So when we talk about the tangent vector, okay, we're talking about r prime of t, and it's useful for us to define the unit tangent vector that's going to be capital T of t, and that is going to be the derivative of r of t divided by the magnitude of the derivative of r of t. So how do we want to interpret this new derivative that we found? Well, the derivative is always going to be the rate of change, so it could be the rate of change of the vector r of t with respect to t. But if r of t is a position vector, of, say, an object, then the derivative represents the velocity of that object. Okay, so if we have a position defined by r of t, then the derivative of position is velocity, like we had in one dimension. Furthermore, we can say that the magnitude of the velocity, so the magnitude of that velocity vector, is the speed of the object. Okay, let's move on to a couple examples. So let's find a vector equation for the line tangent to the curve with a position vector, cosine t, sine t, and t. So this is a helix, like we had seen before. And now we want to find a vector equation for the line that's tangent to that curve. Okay, so if we need an equation for a line, right, we're going to need a point, and then we're going to need a vector that's pointing in the direction of that line. So we have the point, p is -1, 0, pi. We want to know what time that occurs at. So note, at t equals pi, r of pi is equal to cosine pi, sine pi, pi. Of course, the cosine of pi is -1, the sine of pi is 0, and t is pi. So that point, negative 1, 0, 1, occurs when t equals pi. Okay, so we have our point. We're now going to need a direction for our line. So our direction, we want it to be tangent. So we're going to need a vector that's tangent. That vector will be the derivative, negative sine t, cosine t, and 1. And then the derivative at that particular point, pi, will be 0, sine of pi being 0, cosine of pi being negative 1, and then 1. So now we have our vector that's pointing tangent. And so the line that's tangent is going to be the vector 0, negative 1, 1 times t plus the point that we're starting at, negative 1, 0, pi. Okay, one final example. Let's find a parametric equation for our particle that's moving along the parabola y equals x squared in the plane. Okay, so if we want to find a parametric equation or a vector equation for y equals x squared, the easiest thing when one variable y is a function of the other is to let the input variable be t, and then the output is supposed to be x squared, which is then t squared. So that tells us that r of t is going to be t squared. And then we want to find the velocity and acceleration vectors when time t equals 2. Okay, so we want to find velocity. So if we want to find velocity, which I'll write as v, is the derivative of position. So what's the derivative of position? Well, we need to take the derivative of the two components. So x prime happens to be 1 and y prime is 2t. So the velocity vector is going to be the vector 1, 2t. And just like in single variable calculus, the derivative of velocity is going to be acceleration. So acceleration will be the derivative of the velocity vector, or the second derivative of the position vector. That's going to give us, if we take x double prime, we're going to get 0, and y double prime is going to be 2. So the acceleration is constant, and it's 0, 2 for that particular position vector describing the parabola y equals x squared. And so these are a few examples of things that you would want to find using derivatives of a vector valued function.